to have the acro whatever it is, you have to be homozygous dominant.
Oh, so that's actually the p-value.
So that's actually the p-value.
Okay. Yeah, I think I just got those mixed up.
Because again, I just took 1 divided by 25,000, and that gave you p squared. Square root, that gives you p.
Which is 0.002 for p.
Right? I got 0.006. If you square root 0.0004, it should be 0.0063.
There's 5 zeros.
Is there 5? I only got 4.
Oh. You're right.
Is that what you got?
Yeah. The 0.006?
Yep.
Yeah.
And so that's B is 0.00636, whatever. And then C, the heterozygous, which is 2PQ, I got 0.0125.
I got close. Mine's 0.0119.
Okay. Did you do 0.006?
Yeah.
For your B value? Yeah.
Yeah, I did 0.006 and 0.994, so
yeah.
Mine were not as accurate as yours.
Okay.
Sarah, what'd you get on that again?
So 0.0125. And he got that number.
Yeah.
I just carried 1 over sig fig. And then, out of the population of 10 million people, how many heterozygous are expected? I got 125,000.
Did you just do point?
Well, you guys will get 119,000.
Yeah, I got 119,280.
Yeah. Yep. That was just based on how many sig figs you carried.
Okay. And then with 4, I was really confused.
I was confused with C and D, but I got A and B, I think.
Okay. How'd you get A?
So, your IA is your P value, or Q value, whatever you want to think of it. It doesn't really, you can label them however you want, really. And then, so, homozygous IA would be P squared. So I just took that number and squared it.
Okay, so did you get 0.0784?
Yeah. Okay. And then for AB, it'd be like 2PQ.
Oh.
So you 2 times the 0.28 times 0.17.
Okay, so that's. So did you get 0.0952?
Yeah. What did you do, Adam? Is that right?
I didn't get that problem.
Okay. Because in her notes, it says you'll have a P squared, a Q squared, and an R squared. And then you have a 2PQ, 2PR, and a 2QR.
You're right.
And so you assign each one, and then, so that's like the 2PQ.
Okay.
You assign A is P and B is Q.
Okay, that makes sense. And then for II, did you get 0.3025?
Yep.
And then IBI, that would be the 2, okay. So I just need to multiply that by 2. So did you get 0.187?
Yeah.
That makes so much more sense. Okay.
Yeah, I had to look at that one for a little while.
And then, so with B,
so the Japanese population is in question continues. 10,000 individuals. How many of these individuals would have the IBI genotype? And then so you just take 10,000 times the 0.018, which is 1,870.
Okay. That makes sense. And then, as far as like the phenotype frequencies go, I like the possibilities for the A blood type were like IA or IA little I, and And so I just squared 0.28 and then added that to, I guess it would be 2 times 0.28 times 0.55. I'm not sure if that's how you would.
We'll do it. Tell me what you get.
I just need to fix that.
Because I did.
So I got 0.3864.
That's what I got.
So that kind of makes sense.
Because then you just added the two together, right?
Yeah.
Yeah.
And then for the O blood type, did you just get the same frequency
Yep.
as above? Okay.
And same with AB. Because those are the only possibilities.
Yeah.
Does that make sense how we're doing those ones?
I am not really following, but
So if you look at her notes, this one, when you have 3 individuals, so in the 2 circumstance, it's the q squared plus 2pq plus q squared equals 1.
mm-hmm.
When you throw in a third one, you'll have p squared, q squared, and r squared. And then each one of those combined will have its own 2pq. So you'll have a 2pq, a 2pr, and a 2qr. And all those together equal 1.
Oh, okay. So all the p squared, q squared, r squared, and all the 2p and all the heterozygotes are all going to equal 1.
Yeah.
Okay.
And
okay, that makes sense.
And so in this problem, the homozygous A will just be like your p squared. And so you can just square the value they gave you.
Mm-hmm.
And so that's your IAA is just the 0.28 squared. It's your p squared.
That's the genotype frequency?
Yeah.
Okay.
And then your AB is it's your, so if you assign your P to A and Q to B, it'd be your 2PQ.
2PQ, okay.
So it'd be 2 times 0.28 times 0.17.
Okay.
And that gives you your genotype.
Okay, cool. That makes sense. I can go back and do all that.
Okay. And then for problem C, when you get there, the A blood type, there's 2 possibilities. You can either have the homozygous A or the IA little I. And so if you just take your P squared and then your 2PR and you add those together, that's what we're saying. That gives you your ratio, your phenotypic ratio frequency.
Gotcha.
And then the O and AB, since you only have one option, it'll just maintain the same. And so I got 3,025 for D.
Yeah.
Okay. So number 5 was weird too.
Mm-hmm.
I think there's just the 2 genotypes in there.
Yeah, I wasn't sure. So I assigned the MM genotype as P squared, and then MN was 2PQ,
Yep.
and then NN was Q squared.
That's what I did.
And then, but when I was finding the expected counts, I wasn't sure if you were just supposed to assume that 1/4 were going to be MM, 2/4 were going to be MN, and then 1/4 was going to be NN,
That's what I did.
1 to 2 to 1. And then you get I got a chi-squared number of 6.97, which would obviously be rejecting it.
You had 6.97. I had 373.
Okay.
Wait. So what'd you get your expected MM value at?
50.
And then 150?
Mm-hmm.
So it's observed minus expected. So the observed MM was 168 minus 50.
Mm-hmm.
You square it and divide by 50, right?
Oh, I think I divided it by 50 and then squared it. That was my problem. Do you just square the top?
You just square the top.
Okay, that's where.
This is your formula.
Okay. Oh,
Expected minus
okay.
squared divided by expected.
Do you remember this well, Adam?
I try to forget it.
Okay. So let me work this
So
out.
do you remember the formula?
The chi-squared formula?
Yeah.
Not really.
So it's the sum of all your values, and it's O minus E in parentheses squared divided by E. O is observed and E is expected.
Okay, that's right.
And then you have to solve for your expected values, and so you take your Mendelian theory of it. It's going to be like a 1 to 2 to 1. That you'll have 1/4 is homozygous dominant, half are going to be heterozygous, and then 1/4 homozygous recessive. And then you just multiply that value by your total amount, and that's what your expected outcome should be. And then you add all those values up.
Okay.
So where I got confused with this one, like as far as like finding the expected, was we used the the Mendel laws to figure out the expected, but our null hypothesis is supposed to be the population is in Hardy-Weinberg
Equilibrium.
Oh, okay.
So that's how you know equilibrium should be. It should just be a perfect outcome.
Okay.
There's no mutations. There's no mixing of genes.
Okay.
So it should just be Mendel's.
You got 373.56. So obviously it
Doesn't match.
It's not an equilibrium.
So it is not Hardy-Weinberg's equilibrium. And I just said it's possibly due to the fact that they're Eskimos, unless they're moving around a lot and maybe introducing new genes and all those in the gene pool.
And they're also like, I'm sure, I guess this might be like drawing stereotypes, but like it doesn't seem like they're a huge population, so there's going to be
small.
like a ton of like, what is that even called? Gene flow.
Yep.
So that, yeah. And that, so if one person has a mutation, then that's going to go through pretty quickly.
Yep.
Okay.
So really quick, tell me how you find the allele frequencies for M and N.
So we know the total is 200. And so I did.
You want to show them on the board? You can just.
Do you want to do it?
Yeah. I don't know what you would cross though. That's like the only thing. Because if you do, oh yeah, you do MN.
Yeah.
Can you even see this, Adam?
Yeah.
Okay. So
you do a test cross, so you do.
Oh, you do.
That's right. That's perfect.
Right. So I just did like, in an ideal like situation, if it was following the Mendelian inheritance, it would be 1 to 2 to 1. And so to find how many like homozygous dominants you should expect, you just do 1/4 times 200, which is 50. And then for the heterozygotes, 2/4 times 200 is 100, and then 50 for the homozygous recessive.
Was that your question?
So what she's asking for is the expected frequencies, or
No. So the actual number A. Are you asking for number A?
yeah, how do you find the frequencies for those?
So what was the NN? How many NNs were there?
2.
30.
30 of 200.
Oh, NN. Sorry, 2.
There's only 2. So there's only 2 of those in a population of 200. So you divide 2 by 200, and you get a really small number, and that's going to be your Q squared value, and then you square root that, and you get 0.1.
Oh, okay. So that just goes back to the other problems we were doing.
And then you minus it by 1, you get 0.9. So your Q is equal to 0.1, and then your P is equal to 0.9.